Let me now illustrate or introduce a few more concepts, and the first that I want to talk in the context of mass transport before I conclude my discussion is the effective concentration boundary layer thickness and the boundary layer thickness. So, it is a concentration boundary layer and effective concentration boundary layer. Now, you consider a solid, so which is dissolving. So, this is the solid here and this is the fluid, and the flow is in this direction. We are talking about convective mass transport, and this is the direction x. And if you plot the concentration versus distance in this particular system, the concentration goes like it is C sub star S, and then it changes in this particular fashion, and it goes like this. And as I have indicated to you earlier, that the distance where, suppose this, if at this distance, if we say C S star minus C divided by C S star minus C B, what is C B? C B is this bulk concentration. If it is approximately is equal to 0.99, so the location at which the concentration is such that this definition or this criteria is fulfilled, that particular location, the distance from the interface is a concentration boundary layer. Now, if you draw a tangent to the surface at this particular point, suppose this is the tangent, then you see the slope of the tangent, the slope, and this is at x is equal to 0. Slope of the tangent at x is equal to 0 is nothing but, I would say, this is C S star minus C B perpendicular divided by, so this and the delta, this distance, which is nothing but delta. So, therefore, I can say that the slope of the distance, actually this should be, I would say, this distance, suppose this is the distance, and divided by this distance I name as delta effective. So, this distance divided by this distance becomes equal to the slope of the tangent. So, this is, I say, delta effective, or this is dt over dc over dx at x is equal to 0, at x is equal to 0. So, now if you have, for example, if you have seen the definition, the flux I have written is equal to J is equal to D into delta C. Okay. So, therefore, the flux is also is equal to, I have seen this is not is equal to D, this is mass transport coefficient, I am sorry. So, this is J, the flux is equal to mass transport coefficient into delta C, and if you look at it, the delta C remains same and J comes out to be is equal to, J is equal to delta C is the same, which is Km into Cs star minus Cb. Okay. Having said so, I can now on the basis of this clearly show that, before I think I go and derive this further, let us look at what are the mechanisms of mass transport at the surface. So, mass is transport by diffusion. It is by convection, and it is transported by turbulence. So, this is the three different mechanisms of mass transport. Now, when we talk of mass transport, so this is the total flux J subtotal. Now, if I say that the total mass transport from the surface J total at x is equal to 0, then obviously the convection part is equal to 0, because at the surface there is no fluid flow, at the surface there is no turbulence. So, therefore, the total flux is going to be equal to the diffusion flux, which is nothing but d over x. But this is at x is equal to 0. Now, you note that it tends to give you a picture that the mass transport at the surface is diffusion flux, or the mass flux at the surface is solely due to diffusion, but it is not so. Even though the expression looks like the diffusion flux, you must remember, or you must note from this, that the slope of the curve is related to the nature of the fluid flow. You can visualize possibly that if the flow past the solid is very, very fast, this thickness is going to be very, very small. Okay? So, the slope of the curve, which is nothing but whatever I have done there. So, the slope of the curve will depend on the nature of the fluid flow. So, therefore, even though the expression may look like diffusion, the fluid flow does have a role to play when mass transport in the fluid side is concerned. So, therefore, if I can manipulate this equation, total flux, and this is also the total flux, which is mass transport coefficient into the concentration gradient. So, if I manipulate these two, then I can show that the delta effective comes out to be mass transport coefficient. So, delta effective is in distance, which is the slope, which is say has a dimension of meter, and this is equal to the mass transport coefficient or the diffusion coefficient, which is d divided by, or I can otherwise say also Km, or Km, the mass transport coefficient, is equal to d divided by. So, this is, and as you can see that the mass transport coefficient, when you talk about mass transport between a solid and a fluid, is directly proportional to delta and is inversely proportional to delta effective. So, that means the delta effective is this distance. So, therefore, as this distance becomes less and less, the mass transport coefficient becomes more and more, which essentially means this distance will become less and less, provided the current of fluid is past the solid is more intensive. And this is Km proportional to the power d to the power 1 when we are talking of mass transport between a solid and a fluid. But if you are talking of mass transport between two fluids, in that case it is found out that the mass transport coefficient becomes proportional to d to the power half, which one can show from Higgs's model, of course, which we are not discussing here. If you have taken any kinetics course or mass transport course, you know already this. Now, therefore, the effective concentration boundary layer is important for us, okay? And if you know the mass transport coefficient, we should be able to find out the effective concentration boundary layer thickness, or vice versa. Now, in this particular case, for example, as I have mentioned, that how do you calculate the overall rate? So, therefore, either you know the delta effective, or alternatively, if you know the mass transport coefficient, in that case directly you should be able to use this equation, and then you should be able to calculate the rate. Now, as I mentioned to you already, that this Cs star, the concentration of the species which is there in the solid and which is going to the liquid phase, is dictated by the laws of chemical equilibrium and thermodynamics. How? This also I have mentioned, and I will briefly reiterate that the transport of the species from the solid to the liquid phase depends on number 1. First is the interfacial chemical reaction. Once the interfacial chemical reaction takes place, then the transport across the boundary layer, and number 3 is the from the edge of the boundary layer to the bulk. So, the overall process of dissolution we can visualize to be comprised of 3 different kinetic steps: interfacial chemical reaction, which is C at solid is going to C sub and dissolve. That is what is happening. And then we have number 2 is the mass transport across boundary layer, then transport from edge of BL boundary layer to bulk. This step can be assumed to be very fast. So, therefore, we will say that well the concentration really comes to here like this and from here edge of the boundary layer. So, this is really the simplified concentration profile where I am saying that when this kinetic step number 3 does not exist. So, within the bulk there is no difference in concentration, the concentration remains horizontal, whatever reaches here that same species reaches here almost instantaneously. If I say that this chemical reaction or the interfacial reaction is also very fast relative to this, that means I am essentially saying that the dissolution is controlled by transport across the boundary layer, or boundary layer mass transport is the rate limiting step. In that case, okay, this chemical reaction becomes, therefore, I can say that this is now, I can complete the arrows, and this is at equilibrium, and therefore, I can say that this equilibrium essentially implies that we have reached the equilibrium solution, equilibrium concentration of the solid at the surface. And what is the equilibrium concentration? Equilibrium concentration in this case is nothing but the saturation concentration of the species. So, at that temperature where I consider where I carry out the temperature the measurements, I can say I can find out very easily that what is the concentration, saturation concentration level, and therefore, the surface concentration can be, this term can be known. So, therefore, the way the surface concentration, interfacial concentration during boundary layer mass transport is calculated is simply by the application of equilibrium concepts, and in this case it comes out to be that the saturation concentration is the surface concentration, and in this case bulk concentration of course can be taken to be 0, or it can be taken to be changing with time depending on whether the reactor size is much bigger to the dissolving species or not. For example, if I am talking of 150 ton steel bath and I have added 2 lumps of ferroniobium, I can consider that the bulk concentration of ferroniobium possibly is 0.001 or 0.01 percentage, and I can ignore it. So, generally we will calculate, we will consider this to be approximately is equal to 0. This will be obtained from the mass transport from the concept of equilibrium concentration, and the only job therefore which remains to be addressed at this particular point is the mass transport coefficient. And if you consider the geometry to be a flat plate, in that case we can say that shade roots is equal to 0.663 into Reynolds raised to the power half and Prandtl Smith raised to the power 1/3. This can be used to calculate the mass transport coefficient, because this is nothing but Km then L over d. So, having given the velocity, I should be able to calculate the Sherwood's number from this flat plate correlation, flow past a flat plate, and use this correlation to determine Km. And once I know Km, I can multiply Km with the CS star, the solubility limit, and get the net rate of dissolution which I am trying to know. Now, we can say a few more things about slag metal reactions and multiphase controls. So, let us I can also, before I go to that, I can also tell you one more thing, that how thermodynamic concepts are used, how thermodynamic concepts are used to determine interfacial concentrations, to determine interfacial concentrations. I will take the example of the gas carburizing and explain this concept to you, and it will be certain to you that yes, in mass transport analysis indeed the knowledge of thermodynamics is adequate, and the knowledge of thermodynamics and consideration of equilibrium really gives us the avenue to fix concentrations which are used to compute the rate of mass transport. Now, suppose I have a solid and I am using a gas CO2 at a high temperature T, and we have carburization taking place, which is known as gas carburization. So, this is steel which contains, and this CO2 basically decomposes at the surface to produce CO, 2CO, CO2. Now, in these cases, what happens is, if you want to find out the rate at which carbon is diffusing, or the rate at which the case depth means the depth through which carbon is penetrating, okay, noticeable carbon penetrates. So, if you want to calculate this rate, it is necessary for us to have the surface concentration known. Why it is necessary for us? Because if you remember, I have told you that we have to solve this equation in order to find out the concentration profile of carbon. So, we have to solve a differential equation, and in this particular case we will require the boundary conditions that at x is equal to 0, suppose this is x is equal to 0 and this is x is equal to some constant a. At x is equal to 0, we have to know the boundary condition because this is a second order derivative. So, we will require a boundary condition here. Similarly, at x is equal to a, where carbon is not able to penetrate, the concentration for all time remains equivalent to the original concentration level. At t is equal to 0, we need another condition which essentially tells us, which essentially gives us that at t is equal to time t is equal to 0, the concentration everywhere is equal to the homogeneous uniform concentration. So, we need the surface concentration to calculate the rate at which carbon is diffusing, to calculate the case depth here. Now, how do you determine the surface concentration here? The surface concentration here is determined on the basis of, so we have how the process goes on. The carbon monoxide carbon dioxide mixture comes into the furnace, enters into the furnace, then the carbon monoxide reaches the surface. At the surface, this chemical reaction takes place, and thereafter this carbon which dissolves into the solid starts diffusing. So, therefore, we can visualize it, the whole process to be made up of several kinetic steps. The first kinetic step is transport of gas mixture to surface. Number 2, chemical reaction at the surface. And number 3, diffusion of carbon. So, the rate at which carbon or the case depth is growing is a function of the rate of these three processes. So, therefore, I can now make an assumption to say that look, the gas whatever I inject here reaches immediately here. So, this is not the rate limiting step. Similarly, this is a high temperature process. So, I can say the chemical reaction is not rate limiting, it is the diffusion of carbon that determines the rate of growth of the oxide layer. So, I can therefore say that well, this equation which I have written like this, I can represent this equation. It is operating close to equilibrium, and if I write the K equilibrium for this equation, therefore, I will say activity of carbon into PCO2 divided by PCO square. The equilibrium constant is known to me from thermodynamics, from delta G naught known. Now, suppose the total pressure. So, I have this is known, I have 1 unknown, 2 unknown and 3 unknowns. So, I have to have 3 equations in order to find out what is the value of A sub C, or the concentration of carbon at the surface. That is what is this activity of carbon at the surface. So, I can write it like this. You can take it to be wet percentage of carbon, but no matter what you take, it turns out looking at this equation, we need 3 equations in order to find out. If the whole experiment is conducted at 1 atmosphere pressure, then I can say PCO plus PCO2 this is equal to 1. This has to be fulfilled, and finally, I can say that the gas mixture that I am introducing, if it has PCO, PCO2, the ratio of composition is known to me. In that case, the whole purpose is fulfilled. So, I have now 3 equations, and based on these 3 equations I can calculate the surface concentration, and this forms the basis of rate calculation. Finally, before I conclude, I want to show you the slag metal reaction, just show you some figure and explain slag metal transport, so that you understand. If I have a species which is transferring between slag and metal, so this is the interface, okay, and this is metal. Basically, if a species is transported, as I said, that we have slag phase, metal phase transport, slag phase transport, and chemical reaction. Okay. So, I can say that if there is only metal phase transport is rate limiting, slag phase transport is not rate limiting, in that case the mixing or the mass transport in the slag is instantaneous, and the concentration profile looks like this. If I say that both metal and slag transport are rate limiting, then I can say that, well, this can go like this. You must remember that this is the interface. If you plot temperature, then you find at the interface you have a constant temperature, but this does not happen when you plot concentration. So, this is what we are doing is, this is basically concentration, and this is basically distance. That is what we are trying to plot. Okay. So, this, the red line that I have shown here basically represents the slag metal phase control. So, there is some difference, from the interface, there is a boundary layer development. So, there is some resistance across the boundary layer, and the transport is rate limiting, and corresponding red line is horizontal, which essentially means that there is no concentration gradient here, and therefore, the transport in the metal phase is not rate limiting. We have 3 possibilities here: either when a species is transported from the metal to the slag, or vice versa, we can have either the metal phase rate limiting or the slag phase transport rate limiting. Firstly, I would say we can have grossly transport process as the rate limiting, or chemical reaction as the rate limiting. Now, of the transport processes being rate limiting, or if the transport processes are rate limiting, then I can say transport in the metal phase can be rate limiting, or transport in the slag phase can be rate limiting. So, there is possibility of one phase controlling, and there is a possibility of mass transport being controlled by transport in the 2 phases. So, therefore, I can say that it could be there is a possibility of purely chemical control. This is one possibility, that means the reaction controls, and in that case I will draw this particular line. If it is chemical control, then I will see that, well, there is no boundary layer neither in the metal phase nor in the slag phase. The lines are completely horizontal, and this is an indication of chemical control. That means the rate of the chemical reaction is rate limiting, pure chemical control. On the other hand, if I say that mass transport is rate limiting in the metal phase, I will say that, well, this goes like this. This is case 2, which I would say mass transport in metal phase rate limiting, and if I say that this is also like this, that the line goes like this, then I would say this is also a case of mixed transport control. I would say this essentially represents mass transport in slag phase rate limiting. Now, we can have various permutations and combinations. So, if I if I now draw these two lines simultaneously, okay, this line as well as this line, if I draw them simultaneously, then I would say that, well, this essentially represents that transport in both metal and the slag phases is rate limiting. If I draw only one line out of the two, then I will say transport in metal phase is rate limiting or slag phase is rate limiting. On the other hand, if I draw these two lines as horizontal vertical lines here, then I will say chemical reaction as the rate limiting. This essentially also tells us that what this could be mixed transport control, and this nevertheless does not only tell us that there is that chemical reaction is not rate limiting. A similar kind of plots can also be. So, this is a scenario which I would say that when this sort of a condition exists, and this I would say is what is known as mixed control. Mixed control basically implies that more than one kinetic steps are rate limiting. Mixed control also does not tell us that it is whether mass transport is rate limiting or mass transport but chemical reaction is rate limiting. It tells us that more than one kinetic steps are involved in the whole process. These two steps could be mass transport in the both phases rate limiting, or these two processes be such that mass transport in the both phases as well as chemical reaction at the interface. These are both responsible for governing the rate of the process. So, enough is said about mass transport. Now, let us concentrate on the situation when chemical reaction is the rate limiting step. So, I have shown you that if mass transport is the rate limiting step, how to calculate. If it is a diffusion mass transport, you calculate the diffusion fluxes, solving the relevant equations. If it is convective mass transport, you know the mass transport coefficient. So, theoretical framework do exists, as we understand, based on which the rates of the mass transport control processes can be calculated. Now, in those situations where chemical reaction controls the rate, and as I have mentioned to you that basically at elevated temperature, mostly the processes are going to be mass transport control. By the way, how do you find out, for example, whether mass transport is the chemical is the rate limiting step or chemical reaction is the rate limiting step? You have some acid tests, okay, and what are those tests? Suppose you take a reaction and you increase the gas velocity or the intensity of stirring in the system, and if you find that the intensity of stirring does not have any significant influence on the rate of the process reaction, in that case you will conclude that it is not chemical control, and if the stirring has no effect, I repeat, if the stirring has no effect, it essentially implies that the rate of the chemical reaction process is controlled by chemical reaction. So, it is chemical kinetics control and not mass transport control. Okay. On the other hand, if you say that the temperature, if you increase the temperature, the second test would be if you increase the temperature and you find out that if you are increasing temperature, the rate of the process is not changing significantly. In that case, you can say that, well, this process must be mass transport control, because the rate of chemical reaction is strongly dependent on temperature, and we should expect that if you increase the rate if you increase the temperature, the rate of the process, particularly for those where chemical reaction is rate limiting, is controlled extensively. So, we have catalyst. For example, you introduce a catalyst, and the catalyst will have no role as far as the rate of mass transport is concerned, but the catalyst has some role as far as chemical reaction rate is concerned. So, a catalyst can influence the rate of a chemical reaction, but not mass transport. So, using a catalyst, you should be able to find out the nature of the rate limiting kinetic step. So, coming back to the question of calculation of rate when chemical reactions are rate limiting, in that case we must understand that there is no theoretical basis based on which, like mass transport, we should be able to calculate the rate of the chemical reaction. The rate of the chemical reaction is to be predominantly determined by knowing the rate constant, or experimentally determine the order of the reaction and rate constant, and so on. So, it is totally experimentally determined rate that is to be obtained when chemical reaction is the rate limiting step. There is, of course, some theoretical considerations do go in order to find out the concentration driving force for the chemical process, but apart from that, the subject is going to be solely based on experimental measurements. Now, suppose we have chemical kinetics. I will very briefly just mention some of the key concepts. suppose we have, this is a forward reaction, and suppose both of this, a gaseous product A is being converted into a gaseous product B, and I can say that the rate of the reaction is equal to the rate constant into concentration of A raised to the power Na, in which Na represents the order of the reaction. Na could be 1, 1.52 depending on the process. This is the rate constant and this is the overall rate, and this concentration is the concentration per unit volume. This is a homogeneous reaction. A is a gaseous product and B is a gaseous reactant and B is a gaseous reactant. Consider this equation. Okay, we have carbon plus oxygen and producing carbon monoxide. Or we can say that in this case, for example, we have a gas solid reaction. This is again a forward reaction. So, this is now a heterogeneous reaction. This is a homogeneous reaction. A is gaseous, B is gaseous. Here we have oxygen and is gas, carbon is a solid and carbon monoxide is a gas. So, this is a heterogeneous reaction, and heterogeneous reaction as you all know. So, we have the solid here and we have the gas here. So, the site of the reaction is actually the interface. So, these are the sites of the reactions, and as you can see, if you write down the rate in this particular case, I can say that, well, the rates are always to be, I have written the concentration, but because as I have mentioned also that apart from concentration, perhaps activity or chemical potential is far more important, because that represents the driving force. And if I assume that, well, the gases behaves ideally, the activity of carbon is in pure phase and carbon is equal to 1. So, I can then say that it is going to be equal to PO2, and this is based on the supposition that the activity of carbon is equal to 1, oxygen is behaving like an ideal gas, and in which N represents the order of the equation. And this specific rate constants, this order of the reactions, there is no way that for heterogeneous chemical reactions one can determine experimentally, theoretically. So, therefore, the overall rate calculation has to be. Now, when I have shown this equation, which is going from left, it is the spontaneous oxidation of carbon to carbon monoxide. However, if this equation approaches equilibrium, or it is not at equilibrium, it is approaching equilibrium, that means there is a reverse reaction rate also. In that case, the overall rate of the reaction is going to be the forward reaction and minus the backward reaction. So, the net rate of the reaction is the rate of the forward reaction minus the backward reaction, and in that context the expression becomes a little bit more complicated, that we have to deal with two different rate constants, a forward rate constant and a backward rate constants. Now, the rate of a chemical reaction basically varies. Suppose, for example, in order to the Arrhenius, so rate constant, so you can say this is K, and this varies as A exponential minus E sub A divided by. How does the rate changes with temperature? And as I mentioned to you repeatedly, that the rate will change considerably, significantly with temperature, because the temperature increases, energy of the system, and chemical reactions require bond formation and bond breakage. So, they are associated with high activation energy. Okay. So, you have to supply a lot of energy in order to form new breaks, break few bonds and form new ones, because only when you break bonds you will be able to form new ones, and the whole process requires large, and therefore, the rate is dependent on. So, that is how the rate really increases. And if you look at the rate constant k versus ln k versus 1 by t, and then you will see you will get a straight line with a negative slope. So, rate constant k is equal to a exponentially minus E a by r t. So, if ln k is equal to a ln a plus minus E a exponential, and ln will nullify, and therefore, we are going to have E a by 1 over r t, which essentially tells us that if you plot ln k versus 1 by t, you should a straight line, and the slope of the straight line is a measure of E sub a. I am not saying it is equal to E sub a, it is a measure of E sub a, or the activation energy of the process. By looking at the activation energy also, we should be able to find out that whether the reaction process is chemical control or mass transport control. Mass transport control processes where there is no breakage of bonds etc. involved, we will know that yes, the mass transport processes are characterized by small activation energy. On the other hand, chemically controlled processes are characterized by high activation energy or more steeper line when you make an ln k versus 1 by t plot. Now, one important thing here is that the concentration, this concentration that we have introduced here, what is this concentration? In this particular case, the concentration that I have written here is the bulk concentration. Okay, so everywhere there is it is a homogeneous chemical reaction. But now the concentration that I am talking about is not the concentration at this particular location, but it is the concentration at the surface. So, if it is the concentration of the surface, we must understand that the area of the surface will matter, or the size of the particle is going to matter. Okay, so bigger is the size of the particle, more is going to be the effective area, and so therefore, the concentration is going to be affected. So, therefore, the rate of the reaction is going to be affected. So, that shows us that, but it creates some problem measuring, specifying the concentration in terms of concentration per unit volume or amount per unit volume is a very easy task. But how do you know that what is the concentration per unit surface, particularly when the reaction front is changing as a function of time? At 10 o'clock, the size of the carbon particle is this, at 10:15 the size of the carbon particle becomes smaller. So, the area is continuously changing. So, therefore, there is some issue, some problem as far as specifying this concentration at the surface is concerned. But we must understand what I am trying to say here, that the rate of the reaction will depend on the size of the particle. So, if you change the size of the particle, the concentration also changes, okay, because this is the concentration at the surface of the solid. Now, in most of the analysis, and this is the parameter which poses problem, okay, what is known to us is the bulk concentration. So, somehow this equation is to be converted in terms of the bulk concentration by applying of relevant theories, and then this PO2, the surface concentration, is to be replaced by the bulk concentration. So, some application of some thermodynamics, some additional concepts are necessary in order to convert this equation in a form which we can tackle, because we do not know what is the surface concentration at an instant. What we know is the bulk concentration. So, convert this equation which contains surface concentration into any corresponding equation which contains the bulk concentration. Let us look at this particular equation. Say nickel oxide, which is solid. I will just explain this particular point, and then we have hydrogen, which is gas, and then we have nickel, which is solid, and H2O. So, similarly, the rate of the reaction is going to be proportional. The forward reaction, nickel oxide is solid, activity is equal to 1. So, I can say that the rate of the reaction is going to be proportional to the concentration of hydrogen in the system. Now, if you consider this, similar kind of an expression will come, and therefore, we will encounter that, well, the reaction rate will come out to be partial hydrogen, and this is going to be, so this is the surface concentration. I am saying this is the surface concentration. Okay, so this is N1, and that is the rate. So, how to determine the rate of this particular, the overall rate by converting this into is a bulk concentration. So, if we look at the profile, how does the profile looks like? So, we have this is the nickel oxide, okay, and then we have this is a receding interface. This is a topochemical reaction model. Okay, so we draw this line. Let us now look at that concept, how we can determine or write the rate equation in terms of surface concentration and not in terms of bulk concentration and not in terms of surface concentration. And just now I have written on the left about the nickel oxide hydrogen reaction. So, this is what I have intended to drawn here. This is the nickel oxide sphere actually, and whatever is shown here, this distance is the concentration boundary layer. So, the outer solid line represents the boundary layer, and the solid nickel oxide is this. Now, this is the bulk concentration, and as per our assumption that the bulk concentration prevails right up to the interface, and then it drops gradually to a surface concentration which is equal to C sub Hs, which I have represented as partial pressure of hydrogen. If I would have written the same equation as nickel oxide solid plus hydrogen gas is equal to giving rise to nickel oxygen, nickel as solid, and then H2O as gas. So, the rate of the forward reaction is represented in terms of CHS if activity is equal to 1, okay, and then what is shown here is that how the concentration from the boundary layer reaches to the gets to the surface concentration. So, this CH sub S is actually partial pressure of hydrogen at the surface, which I would write that the rate is equal to rate constant K into pH2, and I can say, and if I assume that the rate is first order with respect, in that case n does not. So, this is an assumption. As I said, how do you know that the rate is first order? We have to carry out experiments, introduce more and more hydrogen, and see how does the rate of the reaction changes with the concentration. If there is a linearity between the two, that is an essential indication that the order of the reaction is equal to 1. So, for the time being, if you assume that the rate the order of the reaction is 1, then this becomes the expression, and this is the surface concentration, and which is equal to CH sub S, which is shown in this particular figure. Now, we know that we have a convection through the boundary layer. We have a boundary layer transport theory, and based on which is the driving force. The driving force is this CH sub B minus CHS, and multiplied by the mass transport coefficient gives me the total flux or convective flux of hydrogen across the boundary layer. Now, this surface has very little capacity to accumulate material. So, and that chemical reaction is the rate limiting, and mass transport is not the rate limiting, because we are discussing now chemical kinetics. So, we can assume that whatever the convection current is taking hydrogen to the interface, that itself is responsible, that is exhibiting as the rate of the chemical reaction. So, therefore, I can say that J sub H is approximately, the convection flux is approximately is equal to the rate of the chemical reaction. And if I do the manipulation, of course, I am not going to the details of it, these are available in standard books, and you can see that in that case the overall rate of the reduction reaction, nickel oxide reduction reaction, can be expressed in terms of the interfacial concentration C A alpha, as well as the two rate constants, which are nothing but the mass transport, resistance to mass transport, and resistance to chemical reaction, which are also known as the respective mass transport coefficient. So, I can write this equation. I can write for JH is equal to R, and then for R I can write down this equation, manipulate with the two, and then I can derive at this equation. It is a trivial exercise, and one should be able to do. So, now you see that although my initial rate expression was this, which contains surface concentration, I have been able to modify by using my knowledge of the subject, or write an expression for rate, which is now in terms of C A alpha, or which is actually in this case is not A alpha, which is going to be C H sub A alpha has no meaning. CH sub bulk. So, earlier it is pH2 and this pH2 is basically synonymous to my CH sub S. That is what is the surface concentration. And now I have been able to convert this into this particular expression, and now you see that this has come into the picture. And you can, on the basis of this, you can also plot from this analysis that how does the rate varies as a function of temperature. So, this is the steepest one line which I have drawn. This line essentially tells us about the exponential rate of variation. This is a how does the mass transport coefficient varies. So, this is rate k is equal to a exponential minus a by RT. So, that is what it is, this particular line, and this tells us about the dependence of mass transport coefficient on temperature, which is theta is the absolute temperature in this particular case, and this gives us a situation when we have mixed control and we have how does the rate will vary as a function of. So, initially towards the lower temperature, okay, the rate is more chemically controlled, because this line, as you can see, goes parallel to this line, and at higher temperature this goes to parallelly with this particular line, which is the mass transfer line, and therefore, this gives us a scenario when the rate is controlled by both mass transfer as well as chemical reaction. So, this is the curve of response of chemical reaction rate control processes with temperature. This is the curve for response of mass transport control reaction with temperature, and this is the curve for the response of both mass transport and chemical reaction control with temperature. And the last one, as you have shown, has part characteristics, a lower temperature characteristics, which is akin to the top line or the steepest line, and towards the lower, higher temperature, we see that chemical reaction is now very, very fast. So, therefore, it is mass transport control, and the equation boils down to this. Now, we can also on the basis of this say that look at the, you can find out the value of this, you can find out the value of this, and then you can conclude that which is the rate limiting step. So, whichever phases, whichever steps is going to show the largest resistance, that controls the rate, and these are direct measure of the resistances to mass flow. So, therefore, due to chemical reaction and due to mass transport. So, therefore, looking at the value of Km and Kr, we should be able to conclude that whether mass transport is rate limiting or chemical reaction is rate limiting. Now, the subject is endless. I can go on and on, but I think it is just to revise and give you or remind you of the basic concepts, as you go through the subject of steel making. So, all these things, starting from thermodynamics, fluid flow, heat transfer, mass transfer, chemical kinetics, they are all essential for us, and we have to have good idea of all these subjects in order to handle steel making, topics very elegantly or in a smart way or quantitatively, whatever you can say. So, I mean, we will not be able to perform many design calculations or process calculations unless our fundamental knowledge of these subjects are really adequate. Now, very briefly, one more additional topic which is of quite importance to us is the gas liquid interactions, which is basically I will discuss this later on in the context of secondary steel making, but this is a topic which goes beyond all this and is of prime fundamental importance to us. When you look at oxygen steel making, we have reacting gases, oxygen is being blown into molten metal. We talk of argon starred ladle, we say argon is blown into the ladle. Tundish also we have gas injection, mold also we have gas injection. Everywhere there is gas liquid interaction, and gas liquid interaction is a subject very close to the heart of steel makers, and we have to have adequate background in order to handle or quantitatively tackle the multi-phase nature of steel flows, particularly in gas agitated system. Now, we encounter two different modes of gas injection. For example, one is the submerged injection, and the other is impinging. So, submerged gas injection basically is encountered in ladles, in oxygen steel making converters, okay. Whereas if you go to LD steel making, or if you go to electric arc furnaces where you have lances injecting oxygen at the surface, you find out that gas jet is impinging on the surface itself. Submerged gas injection is very common in ladle, tun dish mold, etc. Impinging gas jets are very common in AOD converters, in LD converters, as well as in electric arc furnaces. And the nature of the gas liquid interaction could be reactive interaction. If oxygen is injecting, then oxygen reacts with metal. On the other hand, if we are injecting inert gases, in that case there is only hydrodynamic interaction and thermal interaction, but there is no material interaction because inert gas does not dissolve. Now, submerged gas injection, you can encounter various. So, you have a submerged sphere or a porous plug through which we inject the gas. Now, we can have phenomena called jetting and bubbling, and jetting ensues basically when Mach number based on the free strip velocity is greater than 1. Okay. And on the other hand, when Mach number is much less than 1 or smaller than, and the velocity is very small, in that case there is no jetting. In that case we get bubbling. Basically, in the bubbling regime we have a gas envelope which forms, and these gas envelopes basically, as you increase the gas velocities, okay, it extends, and ultimately what happens, you get a completely jet core, okay, which looks like, you know, something like this. On the other hand, when you have bubbling regimes, you have discrete bubbles which form, and these discrete bubbles you can say rise. At the limit of gas flow rate becoming very small, the size of the bubble is governed by only interfacial property, and this is, I think, 6 sigma divided by G delta rho, and this is raised to the power 1 by 3. So, that represents the expression of the size of the bubble, and we have, there is a D nozzle here, and this D nozzle, you know, in the case of metal, it takes a, so D nozzle essentially in water models I would take these D nozzles to be the inside diameter of the nozzle. On the other hand, I will take this is the outer diameter of the nozzle because the weighting behavior of the gas in high temperature liquid metal system. So, the small bubbles forming at the orifices are going to be calculated, but these are single bubbles forming at the orifices. Very rarely such conditions are encountered in the system. Now, when we have bubbles, we basically have 4 different regimes. Okay, we have a plume here, and we can say the first regime is going to be, you know, it is the momentum region where the momentum of the jet gas is going to be filled. Then we have something like transition region, and then finally we have buoyancy region, and lastly we have surface region. So, these are the 4 regions in which the flow rates and the flow regimes are going to be characterized, and we have momentum region, gas voidage is very high, more than 10% or so. We have transition region where the gas voidage is less than 10%, and buoyancy region approximately 2 to 5%, and again the surface region we have a very small gas voidages. To know the characteristics, so basically large part of this system is buoyancy. So, therefore, when the Mach number is much less than 1, the free stream velocity is much less than 1. I will also discuss later on, but the gas is injected, as I have mentioned, either through a nozzle or a tuyere or through a plug. And when you have buoyancy region, you know, occupying the major part of it, at low flow rate when the Mach number is equal to much less than 1, we can say that these systems are basically buoyancy driven systems. One important characteristic comes when you have we are injecting a reacting flow and then you have small shallow bath depth. Ladles and all have bigger bath depth, but when you have shallow bath depth you have swirling motion. So even though this configuration looks like a two-dimensional configuration or an axisymmetric configuration, when you have shallow bath depth and injection at high rate, you can introduce lot of swirling flows or rotational flows in the system, which can aid in mixing in the process itself. And in OBM converters, this is very commonly encountered. So coming back to the buoyancy driven plume, there is a number called the modified Froude number, which is very, very important, and this modified Froude number basically G d to the power 5 dn to the power 5 u square, okay, and delta rho. And this Froude number is inertial to the buoyancy force, and this is a very important number in order to find out the characteristics of the particular system itself. So the modified Froude number is used in order to determine or know the state of the system when submerged gas injection is used. Finally, very briefly about the impinging gas jets. When you have impinging gas jets on a system, for example, you have a nozzle, particularly when you have a LD converter, you have different kinds of a nozzle here, and that different kinds of a nozzle means you have a tube and then you have a 6-hole lance or something like that, which distributes the molten metal. So there is a core of the jet, and then following the core you have large scale entrainment, and so the considerable widening of the jet takes place, and this widening of the jet ultimately impinges here. So by controlling the height of the nozzle, you can control the depth of this penetration, as well as you can control the impinging area itself. The core is very, very important to us, and this core basically is about 3 to 8%. And what is this core? This is the supersonic core of the jet, and this core is 3 to 8% of the jet nozzle diameter. And there are technology today available like the cojet technology, which can enhance the length of the the potential core of the supersonic core of the jet to a significant extent. But beyond the supersonic core, you have large scale entrainment, as a result of which the jet diameter increases, and once the jet diameter increases, its momentum gets distributed, and by the time it strikes the molten metal surface, its kinetic energy has died down significantly. The two important parameters which determines the extent of stirring and the dynamics of the system are the cavity depth and the cavity diameter, and these are characteristics of the gas injection. There are empirical correlations etc. available. Okay, you may have a very hard blow, and in that hard blow you should be able to drive out lot of molten metals in the form of droplets and so on. So one has to have quite a bit of knowledge of submerged gas injection as well as impinging gas jets in order to tackle or handle the multi-phase nature of the steel making system, particularly when one talks about the gas liquid interaction, the level of agitation, the droplet formation, and all these kinds of issues. Okay.